And you probably wouldn't exist very long because the force of gravity, even for that short amount of time, would be in the order of magnitude of like 10 to the 7 or 8 times larger. And your body couldn't sustain that. So after a certain amount of time, it will just turn back into your regular old up quark. So there's this idea of spontaneous existence of particles. So particles can change, or in empty space that has just free energy, there can, for no reason at all, be particles that spring into existence. So let's say an electron and a positron, so anti-electron, and then they'll clash and emit light, or in the case of a photon. And so you'll have all this spontaneous generation of particles. Well, a cool thing is with an electron, it's technically constantly giving off particles that may or may not exist. And it's giving off photons that have zero energy. So looking at this, if it has zero energy, what's the constraint on the time? Is there any constraint? No. Because you have zero energy times anything that's zero, and it has to be less than that constant. So you have these photons that are going off in all directions from your electron, and there's infinitely many photons going off for infinity distance because they're never required to stop existing. And that's why with your electric force, it can act on every particle in the universe, eventually. It's limited by the speed of light, or the propagation of any field. But essentially that's what's happening. And with the strong force, when you have red, green, and blue, inside there's gluons. And the weird thing is they all act towards the center of the trio. Let me get a different marker. But they all act towards the center in what are called flux tubes. But those interact via gluons, which have no mass. So they effectively have infinite time to travel between quarks and cause an interaction. And as far as we're concerned, they're virtual. They never affect anything else. They only ever exist just to mediate the force, and all of the other ones that are never used may as well never exist because we never see them. They never have any effect on the universe other than to move some other particle. But the weak force gets weird because with the weak force, the particles that mediate it have mass. The W plus and minus boson and the Z boson have mass. And remember from our equation equals mc squared, if there's mass, there's energy. So we have a particle that has mass, so it's not traveling at the speed of light, and it has mass, so it has energy. Is it limited in the time it can exist?
Yeah.
Right. And since even light travels at a finite measurable speed, does that mean since we have a finite time for this thing to exist, that it can only travel a certain distance?
Yeah.
You get how that makes sense?
Yeah.
So you have, let's say, some particles coming up, and they're going to go up, and then they're going to bounce off. There's going to be one particle, and it's going to emit a W plus boson. And then once it hits a certain distance, it's existed it's existed up to the limit that it's allowed to exist by the fundamental laws of the universe, the random laws of the universe. And that's going to split off into two other things, both carrying energy. So this boson has a finite range of the weak force. So it's not like gravity or electromagnetism, where it can affect everything in the universe. It can only ever affect things close to it. And so therefore, it can only decay other stuff within a finite range. So that's the dealio with these. All of these carry charge. And there's also gravity, which is mediated by what we call the graviton. There's two reasons that we don't include that in the standard model. Can anyone tell me them?
We haven't found it yet.
One, we haven't found the graviton yet. We've never actually observed it. What's the second one? What?
Isn't it because it's like a one-way force?
It's not because it's a one-way force. I mean, we're not going to discriminate on the basis of that. The gluon is a three-way force, and the electromagnetic is a two-way force. And I have no idea how the weak charge works. Cool thing, which I'll talk about in a second, is that it's actually related to the electromagnetic force, sort of. But can anyone tell me why gravity is not on the standard model explaining physics as we know it? It's because we don't know how it works. We don't know how gravity works and how it relates. Theoretically, we assume that if we have a particle with mass, it's constantly giving off an infinite number of gravitons. And if that isn't how it works, then we really have to revise a lot of stuff. But essentially, we don't know how to relate gravity to the strong, the weak, and the electromagnetic forces, so we can't put it in our standard model. This defines how our physics works, and we don't know how physics works, so we don't put it in. Let's see. Does anyone know who Steven Weinberg is? Nathan. I'll have you say it.
He was at UTA.
Yeah, he was at UTA, I think, at the beginning of last year.
Famous. I forgot what he did.
He was famous
Yeah.
for two reasons. One, he was one of like 7 people in the world that actually understands relativity. And two, he got a Nobel Prize with a couple other people for proving that the electromagnetic force and the weak force actually come from the same thing. And they called it electroweak theory, where they're actually related, and you have something called isospin. I'm not going to draw on the board because I have no idea how to draw this. But at an early point in the universe had a lot of energy, and so everything sort of acted the same. A lot of these particles behaved identically to one another, so that separation between them didn't exist. So you could have electrons paired with muon neutrinos. Could you guys keep down in the back? Thanks. And eventually, what happened is as energy got energy got less dense, there was a symmetry breaking, and that the two of these fundamental forces, the electromagnetic and the weak force, split apart and started acting differently from one another. We actually have a parallel for that we can observe now. The electric and magnetic forces. We know that those act differently, but they are fundamentally the same force. They're the electromagnetic force, which is mediated by the photon, and they interact with one another. So you have a changing electric field that creates a changing magnetic field, and those interact with each other, and then we get a light wave with those two just constantly interacting with each other in a straight line. And what happens is at high energies, they're essentially the same force. So you have the electromagnetic and weak force, and they can interact with each other. So the next force, just going forward with it, they're like, hey, this is cool, let's see if all of the other forces are related. They're starting to find that the strong magnetic force is related to the electroweak force. And there are a lot of scientists going for what they call a grand unification theory, or a gut theory. They haven't found it yet. Mathematically, they can't prove anything. There's a lot of conflicting theories. But that's what they're going for. And then gravity, I'm going to go ahead and draw a timeline of the universe. But gravity is so unlike all the other forces. I mean, think about it. It has one pole, while all the others have 2 or 3. That they can't explain why things happen as they do. So we know that there's electric and magnetic, or electromagnetic forces. And then sometime in the universe, that split apart from the weak force. There's a symmetry breaking in how they acted. And then, as we go along, we found that a long time ago, very near the Big Bang, the strong nuclear force split apart from behaving the same as those. And even longer, almost instantaneously after the Big Bang, gravity acted the same as all those. And so all four of these forces were the same exact force. And then they broke apart from each other. Scientists have no idea how or why, which is one of the cool things of science now, is that we get to go figure out why all this is true. Let's see, other things I can talk about. You guys want to figure out why things behave randomly, why these two equations exist, and why we have quantum mechanics that makes no sense in an actual classical sense, an actual like common sense thing. So I'll give you an